Okay, Calc BC, Unit 3, Day 6. We finally get to do something new in this unit. So we've done a bunch of review, but now we're going to do parametrics for the rest of it. Now, some things that we're reviewing will come in handy, so that's why we did review those things. Here's a problem that's actually from last year. So this is a little review, rectilinear motion. That's 1D motion, one-dimensional motion. And that's what you cover in Calc AB. So we'll just do that, and then we'll start talking about two-dimensional motion. It's a lot of the same ideas. So here's a little refresher. This one deals with gravity. So this is position height with gravity acting on an object. So it says ball is tossed upward from ground level. That's your initial height. At 48 feet per second, that's your initial velocity. And this is using gravity, which equals negative 32 feet per second squared, is the force of gravity in English units. So for us, it's going to be feet. But so our first equation, ST equals negative 16 t squared plus 48t. And then your velocity equation is the derivative of that, negative 32t plus 48. And then your acceleration equation is the derivative of that, which should, if it's gravity, always come out to just negative 32. We're going to do plenty of problems without gravity, so that's not going to always happen. Now, if you want to find the maximum height, that's an EVT problem. So we should use extreme value theorem, maximum. We're trying to maximize something. We have all the equations, which I think is always a good first thing to do. Just get your equations. Max height is S, or Y would be a common variable for position if it's a vertical up and down position, X if it's a horizontal motion. But we need to take the derivative of the thing we're trying to maximize, which, by the way, happens to be velocity. And we found it, negative 32t plus 48. And we're going to set it equals 0 and find critical points. And so we get a t equals 48 over 32. We could reduce that to 3 halves. So this is our critical point. We should find endpoints. So endpoints for time, generally 0 is an endpoint on these time problems. And then the other endpoint right here would be when the object hits the ground coming back down. Otherwise, it would go through the surface of the earth, all the way through the earth, unimpeded. So what we usually do is we say, well, how do you find impact? You set position to 0. So we're going to do that. Negative 16t squared plus 48t equals 0. We can factor negative 16t out, t minus 3. And we get t equals 0 and t equals 3. So you're usually going to get two answers from these gravity problems because they're quadratics. And if it starts at ground level, then you get ground level. But this is when it hits the ground on the other way. Now, if you start at a higher level than the ground, it's going to give you a negative time as if it started at the ground level originally, even though you started from another height. So that's going to be your other endpoint. And so then we would make a table, plug time in, plug our endpoints and critical points in, and we're going to plug them into the original position equation, negative 16t squared plus 48t. Now, when you plug 0 in, it gives 0, which makes sense because that was the initial height. When you plug 3 in, you should get 0 because that's how we found 3. It's a good double check, I guess. Plug 3 back in, you should get 0. 3 halves is going to be 9/4 plus 48 times 3 halves. And so that's going to be negative 36 plus 72, so it's going to be positive 36. That's your max. These are your min. Okay, and so then we'll write an answer the way we usually write answers for absolute maxes, mins. We'll say, the maximum height is 36 feet. Use units at time t equals 1.5, 1.5, 3 halves, whatever. Seconds, those are the units of time, by extreme value theorem. Okay, that's the name of the theorem you use. So how does it work? By checking endpoints and critical points. So in general, I want you to justify your absolute max min answers. I'm going to expect that on your next test. Some people won't do it, and I'll take off points every time they don't do it. But it's something that you guys should be kind of used to doing. I mean, I've been doing it a long time, since last year. Okay, so that's A. Part B says velocity impact. Time of impact. So we actually found that. So this right here, this was our work for part B. And then part C is velocity impact. So we're going to plug in 3 into our velocity equation. And we're going to get negative 96 plus 48. So we're going to get negative 48 feet per second velocity units. Okay, and it's negative, which makes sense because the object, the ball, is coming downwards when it hits the ground. So it should be negative. Okay, so that was just a little review. Now, what we're going to do this year, just to make things a little more interesting, I mean, we did that last year, one-dimensional motion, that the objects were just going straight up and straight down. But what if we throw it at an angle? Like initially, it's at an angle of, 30 degrees or something, angle to the horizontal. Now, with gravity, it's going to kind of go like this, okay, right? It's not going to just be going up and down, but it's going to be going sideways. And so we, how do we do this? This is motion in 2 directions now, 2 dimensions, okay? And this is what parametrics is. It's motion in 2 dimensions. One of the things we're going to do here is this is the initial velocity, 48 feet per second. Let's say we're just using the same, example up here of time 0, but part of it's up and down and part of it's left and right. So these are called these vectors. So if you've taken physics, you've maybe dealt with this before. So this is a 30, 60, 90. We could use our knowledge of 30, 60, 90s. This is the hypotenuse. The short leg is half. The long leg is the short leg times root 3. So this is the initial velocity. This is the initial velocity in the x direction. This is the initial velocity in the y direction. So we're going to have to set up, we're going to have to set up different equations for each direction. And it's going to be a lot of the same work, but just twice as much. Now, I'm going to go over some common just parametric equations today, and you'll get some practice on your homework. So let's see, x and y are functions of a third variable time. So this is usually how we describe parametric motion, is we get 2 equations, one for x, one for y. And they're both dependent on time, just like our motion problems last year were dependent on time, but they were just x or they were just y. And these are your endpoints for time. So the main thing is we got these 2 different ones. Now, when I say what is this, I mean what kind of shape is this graph going to be? And so this is sort of an interesting challenge, and I'll show you guys how we do this. Now, we'll probably once we've done this one, start just jumping to part C first. But one of the things that I might have you do is just make a little table real quick. And this is just to get a couple good points. Now, the starting point is really important, and the ending point is really important because that's going to tell you it's going to be a shape, but it might just be part of a shape. And then you want some point in between. So you just might pick something easy just to kind of identify where the rest of the graph is. And so you're getting x and y values for each of these times. So you plug 0 in. For here, you get -4, 0. So the first point is at -4, 0. It's right here. And what we call this, and we're going to be making graphs like this on the homework, what we call this is we call this the initial point. It is, at the earliest time on our time interval, okay? And then if we plug 3 in, we get 2, 9. So 2, 9 is what we call the terminal point, so the ending point. So these are things that I'm going to want to see on your graphs on today's homework that I want labeled and I want named. Okay, now we just plug another point in between somewhere and see what it gives us. And it might help you kind of see what the shape of the graph is, but there's nothing specifically important about this. Now you might see, okay, there's kind of like a curve here, maybe, but it's going to be easier to identify that if we find the Cartesian equation right from the beginning. Okay, so we already found the initial and terminal points. That's pretty easy to do without knowing the shape of it. So the initial point is -4, 0, and the terminal point is 2, 9. Okay. The direction is going this way. It starts here, ends here. So the direction, you can use the start and end points. Now, find the Cartesian equation. Cartesian means y is like a function of x. Y as a function of x instead of x and y. So one equation for this curve, kind of like what we usually do. And we're going to get some shapes that we've seen before. So what we're going to do is we're going to kind of try and solve this system of equations to eliminate the t's and get it purely with y's and x's together. So what you're probably going to do is say, okay, well, if I get, t by itself from the x equation, right, and then I can plug that into the other equation where I see it with the y's, and now I have an equation that's y in terms of x. Now, what kind of, another tricky, so now what kind of equation is this? I mean, we could go with that. I mean, we could probably write it like this. This might be a little more friendly. I mean, you could FOIL it out. I don't think that's necessarily helpful, but what kind of shape is this? This is a parabola. Okay, so that's the shape, which is something you might be asked to identify. What kind of shape is it? It's a parabola. And it's a parabola that's been shifted to the left 4 units and multiplied by 1/4. So usually we go up 1 over 1, but we're going up 1 over 1/4. And that's the vertex right here, right? Which is actually the initial point. Usually we go up 2 over 4, but now we're going up 2 over 1. So the graph looks like, we could plug 0 in and it's 4. The graph looks like this. The whole thing. But for us, it's just going to be this portion of the graph between the initial and terminal points. So it's a piece of a parabola. Okay, and then that's the direction. Okay. So what portion of the graph with the Cartesian equation is traced by the parametrized curve? So the parametrized curve was what we first had. The graph of the Cartesian equation, that's the whole parabola. And so what we're going to say is it's part of the right half of a parabola or something. sometimes it'll be like much more the whole half or the top half or the bottom half. So that's what we're doing. And on these future problems, I think I want to try and find the Cartesian curve first, because that just makes everything a lot easier. There's no reason to wait if it makes everything make more sense. So I'm also going to show you a bunch of other common shapes we get. So that's a parabola. We're going to see circles, ellipses, lines, hyperbolas. So these ones, a lot of these have sines and cosines in them. You notice several of these circles, ellipses, and hyperbolas often have trig in them. And so I'm going to show you the trick for getting the Cartesian equation. I'm going to start with part C. Okay. And what we're going to use is we're going to use the Pythagorean identities. Now, the Pythagorean identities are pretty common. The most common is sine squared plus cosine squared equals 1. There's two other versions that you can get from this. I don't memorize them because I'm afraid I'd mess them up. I probably would. I don't use them enough now. I remember this one, okay? But now if you divide everything by sine squared, you get 1 plus cotangent squared. 1 over sine squared is cosecant squared. So this is another version of the same thing. Or if you divide the original equation by cosine squared, you get tangent squared plus 1 equals secant squared. So these are the Pythagorean identities. And so you should be able to write them from memory. I wouldn't memorize. I would just remember the first one. And so we're going to use these ones that have sines and cosines. We're going to use this to bring them together to get rid of the t's and get x and y all together. So in this case right here, we're going to solve for sine. So, sine equals y over 2, and cosine equals x over 2. So we're going to plug those in to this one. Now, if we had cotangent cosecants, then we would use the second one. If we had tangents and secants, then we would use the third one. So we're going to use this one and plug them in. So we're going to get y over 2 and get squared plus x over 2 and get squared equals 1. And now you have a Cartesian equation. Now, this should look kind of familiar. Usually we put the x's first and the y second if they're both positive. But this is a circle. It's kind of like an ellipse, but the size in both directions is the same, so that's a circle. So what we usually do is we multiply it through to the other side and write it like that. So this is the Cartesian equation. Okay. And it's a circle, but it might not be the whole thing because this is our domain. So what I'm going to do next is make a table just to kind of see where we're starting on. So we could sketch the circle right now. We say, okay, well, I'm going to try and make use of this graph more. So we could go ahead and just do a rough sketch of the whole thing. I would do it lightly. And then it might be the whole thing, but let's wait. So I'm going to plug these in. We're definitely going to plug 0 and 2 pi in. I'm going to leave some room here. So if you plug 0 in, cosine 0 is 1, so it's 2, 0. So the initial point is right here at 2, 0. That's your initial point. Okay? And so, that's the answer for part B says, we're going to find the initial point and the terminal point. So I want it on your graph labeled, but I also want it written in like the answer column on your test or box in your homework. Labeled initial terminal. So this is 2, 0. The terminal point, you plug 2 pi and cosine 2 pi is 1. You get, it's the same thing. So the initial and terminal actually end up being at the same place. So it starts and ends there. Okay? All right, how about some points in between? We could do pi. Cosine pi is -1, so that's going to be -2, 0. So that's over here. Now, it's hard to tell. Does it go around the circle? Does it go counterclockwise? Does it go clockwise? Little tiny changes in this can make it switch directions. Okay, so maybe plugging in something else in between, like pi over 2 and 3 pi over 2 might help. So pi over 2, cosine pi over 2 is 0, 0, 2. So this is 0, this is pi over 2, this is pi, 3 pi over 2 ends up being 0, -2, so that's down here. So it's definitely going this direction. So I'm going to draw a little extra just line around it with an arrow showing the direction. Okay. And then it is the whole circle because it starts here and it goes all the way around. And that table, just calculating some values, I think it should help you feel very, confident that it is tracing the whole circle. But plenty of these problems will only do like half the circle, or they might do the circle twice or something like that. So for A, I'm going to say it's going counterclockwise. So on these circular shapes, using clockwise or counterclockwise help. B was initial and term points. C was the Cartesian equation. And so, I guess that was that it? Oh, D, what portion of the graph? So D was like, what shape and how much of it. So D is, it's an entire circle once now, because we're going to see somewhere they like get traced over and over on top of themselves. So there you go. So with a lot of these, like I said, we're going to use these trig identities. So the next one, you don't even need to know what shape it is going into it. I wouldn't try and memorize that because it can be really hard to tell. But we're going to say, okay, well, cosine t equals x over 3 and sine t equals y over 4. So we're definitely going to use that first Pythagorean identity, trig identity. So we're going to get y over 4 squared plus x over 3 squared equals 1. So it's going to be y squared over 16 plus x squared over 9 equals 1. And usually you put the x's first, but that doesn't have to happen. And so this is your Cartesian equation. It's an ellipse. Okay, it's like a circle, but they have different sizes in the different directions. Let's go ahead and do a quick sketch of this ellipse. So you're going to go to the right 3 and to the left 3, the square root of the number underneath it, and then you're going to go up 4 and down 4, square root of the number. And you could draw a box to help you kind of like sketch it better. I find this kind of helpful sometimes. I got to fit it right inside the box, and that kind of gives me a little more ability to kind of make it look right. Now we don't know if it's the whole thing, so I'm doing it lightly. So the next thing I'm going to do is I'm going to make a table which will help me find the initial and terminal points and also help me do a lot of other stuff. So I'm going to plug in 0 to 2 pi. That's going to be 3, 0. So 3, 0 is your initial point. And as you plug 2 pi, it's going to be 3, 0 also. So it's also the terminal point. So I want it labeled on the graph. I want the coordinates. I want the name. So I'm going to go and write this initial, terminal. It's going to be 3, 0 for both of them. Okay. Let's do some points in between. Pi, that's going to be -3, 0. So that's going to be over here. And then, let's say pi over 2. Cosine pi over 2 is 0, 4. So it's definitely going from here to here to here, and I bet this is going to be at 3 pi over 2. So that's going to be 0, that's going to be -4. So yeah, it's definitely, and I think it's the whole shape. And the direction is going like this. So I need that on there. Okay, and we're going to go ahead and say what the direction is. It's counterclockwise. I want it shown on the graph. And it is an entire ellipse once. You're going to see some other shapes that are not the entire shape, top half, bottom half, left half, right half, or just a quarter of it, or it might be the whole shape twice or 1.5 times. So there you go. Let's do another one. So now this one you'll notice doesn't have any trig. Parabolas don't have trig, lines don't have trig. So this is, I'm going to use the same trick I did on the parabola on the front to get y in terms of x. So I'm going to say, okay, let's get, t equals x over 3, and then you could plug that into here. And so y equals 2 minus 2 times x over 3. And then we might write this a little more friendly. Y equals -2/3 x plus 2. So this is the Cartesian equation. It is a line. We could, so this is part C. Now this one right here, if we make a table for that, there's no endpoints. It's actually the whole line. It goes forever. Anytime you plug in, you get new points. It's the whole line. So it starts at 2. It's down 2 over 3, down 2 over 3, up 2, left 3. So it's the whole line. Arrows on the ends. Okay? And there's no initial terminal point. Now you could plug a couple points in to figure out the direction. Is it going left to right? Is it going right to left? It could do one or the other. Now I'm going to go ahead. This is the whole line. A segment is a piece of a line. You could also get array. Now I'm going to create a new problem right here and say, okay, well this is our domain. Let's do that. So I'm going to make a table. Plug initial and terminal points. Plug 0 in, you get 0, 2. So 0, 2 is your initial point. And then if we plug in 1, we get 3, 0 is your terminal point. And I think it's that the direction should be obvious that it's, well, not necessarily. Sometimes it can go out this way and come back in the other way or something. So why not? Whatever. We'll just plug no point in between. 3 halves, 1. So it's 1.5, 1. Perfect. So this is the answer, just that line segment. The direction is going from initial to terminal. Okay. So B, initial, terminal, 0, 2, 3, 0. A, the direction, it's going down, left to right, you'd say. And D, it is a line segment. This one is. The original one was just a line. The original one was a line, but this one's a line segment. Piece of line. So there you go. Okay, last one. I mean, I'm telling you guys what kind of shape it is, but hopefully, don't try and memorize which ones are which, but you should recognize them once you get it. Now the main idea here is that we're using those trig identities. So this one is secant and tan. Now I don't know, at least for a while, see if you can write these down from memory, at least the first time on your homework, and then maybe use them again and again. But you should be quick at these. Sine squared plus cosine squared equals 1. Divide everything by sine. divide everything by cosine squared. I mean, I can crank these out pretty quick. So this is the one we want to use this time. So we're going to plug in tangent, which is going to be y over 3, and then square it. We're going to plug in for secant, it's going to be x over 2, and then it's going to get squared. So now this is y squared over 9 plus 1 equals x squared over 4. Now, we usually want, with these conic sections, we want the x squareds and y squareds together. So you could say, well, I'm going to bring the x squared over here by subtracting it, and then you want the other number over here. We want this to be a 1, but not a negative 1. So you really should divide by negative. And then it's actually positive x squared minus y squared, which makes a big difference on your graph. So this is a hyperbola. It's a hyperbola because they have the x squareds and y squareds have different signs. And whichever one's positive tells you which direction it's going to open in. Because what we do next is we say, okay, to the right 2, to the left 2, up 3, down 3, just like we do for ellipses. And draw a box. Now this time I think the box is even more important. Because what we're going to do is we're going to connect the corners of the box with a straight diagonal line, and those are going to be slant asymptotes. So I need those on the graph, and they're going to help you make your graph better. Now they either open up and down if the y squareds are positive, or left and right if the x squareds are positive. So we can go and just lightly draw it in. This is the right and left one, but it might not be the whole thing. So this is part C. So I'm going to make a table, plug time in, get x's and y's. So we'll plug in 0 and 2 pi, plug 0 and now remember secant is 1 over cosine, right? And tangent is sine over cosine, because I don't memorize values for secant, cosecant, tangent, cotangent. I just remember everything in terms of sine and cosine. So you plug 0 in here, cosine 0 is 1, so you get 2. Plug 0 in here, you get 0. So 2, 0 is the initial point. So I want it labeled on the graph. I want the coordinates written. Okay. And then if you plug 2 pi in, I think we get the same thing, 2, 0. So this is also the terminal point. Now this one's kind of more interesting. So it starts here and ends here. So does that mean it goes through the whole shape? Well, let's just plug a couple more values in here. Pi, if I plug pi in, I get negative 2, 0. So it does end up over here, halfway through it. Okay, how about pi over 2? Pi over 2, that'd be division by 0. So that's going to be like infinity, undefined. And then this one is also going to, so pi over 2 is infinity, infinity. And what that means is it's probably like on one of the slant asymptotes, because what happens is this whole curve, even though it looks like two separate pieces, is kind of connected. You can go from one piece, go out, and then come back in on the other side. That's what these shapes do. 3 pi over 2 is going to do the same thing. I mean, it's going to be 0, division by 0, right? Undefined. And sometimes that'll be one of your endpoints. And so you'll realize that the graph just stops after it goes out towards that asymptote. Now we could throw a couple more values in there just to see, like pi over 4. That'd be root 2 over 2, which remember is also 1 over root 2. So that'd be 2 root 2. And then here, that'd be 3. And 2 root 2 without a calculator, see if you can estimate it. It's also the square root of 8, which is between 4 and 9. It's between 2 and 3. It's closer. Maybe it's like 2.8 or 2.7. So this graph should end up looking right if you got a close rough estimate. 2.83 would be like right there. And by the way, that one's right here. So I think it's going out this way towards this slant asymptote. We got to put arrow on it, so it's going out that direction. And then if you were to do like say 3 pi over 4, that would be that would be quadrant 2, so that would be negative 2 root 2 and negative 3. So that would be negative 2.8, negative 3. That would be like over here. And so I think it's coming in this way. And then it probably, I'm just predicting it, we could calculate some more points, goes out this way and then comes back in this way. Okay, so it's going out and then like that. Now we need to put arrows on the ends of all of these, which do not indicate direction. They just indicate that the graph keeps going forever, which it does, and your graph needs to reflect that. So let's see, A was, what's the direction? Like up to the right at first. And B was initial and terminal points. So initial and terminal points are both 2, 0. You'll get some more interesting ones on the homework. And then D was like what shape? It's an entire hyperbola once. But this is all the stuff I want to see. This is all the work I want to see. This is the way I want the answers written. This is the way I want the graph written and labeled. This is what I'm looking for on tonight's homework. And then, of course, eventually your test. Now, for the homework tonight, I've decided to cut off a couple problems just to make it so you don't need to do 25 and 35. So I took off 2 of the 11 problems now. I think there's 9 problems left. They're all odds. Check them in the back of your book. They're your current BC book, the orange one, with the author Kennedy. There is one more problem I can show you real quick. This will help you on a home problem. Given 2 points on a line, so this is kind of find the parametrized equation. So this is like what we're doing, but backwards. So you're trying to find the x and y equations with time. And so I'm going to tell you the times and the points. So at time, this is like initial and terminal points. Okay, or they're, yeah. So any 2 points with the times. So what you do is you say, okay, well, x is going to be it's going to turn out that lines, usually equations for lines for x and y both are linear also themselves. So x is some value, some slope times t plus some value. Y is some other slope times t plus some other value. So I'm just making up some letters to go in here, but this is our kind of our template for it. And then what we're going to use is we're going to use this information. This is x, y pairs that go with certain times. So if I plug in times 0 and x equals 1, I get, c equals 1, right? And if I plug y equals 2 and time equals 0 in, I get, d equals 2. So I have part of what I need. Now I'm going to use this next one, but I'm going to go ahead and plug in what I have so far. So x equals negative 2 equals a times 1, and I found c was 1. So now I could say, a equals negative 3. And I could do the same thing here. The y value is 5. The b times the time is 1, plus d is 2. So b equals 3. So now I could rewrite the equations. I'm going to say x equals negative 3t plus 1. Y equals 3t plus 2. You also need to give the domain for the time. So parameterized equations are the x and the y equations with also the time values. So that's, you're going to have a problem like that in the homework. So there you go. Try the problems. Check your answers in the back of the book. Make some nice graphs and show all this work.